All right, so let's solve this here. It should have been pretty easy, right? I will rely on some of, actually I probably have somebody did the mapping on here, so I can just cheat off of their mapping. Nick, did you map correctly?
Probably not.
Well, not your. I just need somebody who wrote the alphabet out. All right, here we go. Yeah, I think I can, well, I can trust the enters here. It's good enough. Why'd you only go to 33? I guess technically that would have been legit, seeing as though all those characters are legal. All right, this will work for me. So we have elephant plus bear. Okay, so a T plus an R. A T is 29. An R is 27. So 29 plus 27 is 56. Right? How many times does 33 go into 56? One time. With what remainder? 56, 46, 36, 26, 23. Remainder 23, which is an N. Uh-oh. N plus A. Well, an A is a 10, and N is a 23, right? So that's 33 plus 1 is 34. How many times does 33 go into 34? One time. With remainder what? 1. A is 10, E is 14, that's 24, plus 1 is 25. How many times does 33 go into 25? 0. With remainder, 25. And what's a 25? It's a P. H is 17. Plus B is 11, so that's 28. Plus 0 is 28. How many times does 33 go into 28? 0 times, with remainder 28, which is a S. The rest of them we can just drop down, ELEP, ELEP. Ooh, ELEP's been, look right? That's what Yenter got. Did you do it right? No. Make sense? Yeah, it's interesting that that's actually kind of a cool, that would be a good WoW character name. Or a human child name.
I'm down for the human. You gotta have to make sure that the 1 is actually in there. Yeah.
Correct, yep. I don't know, some people name their kids some pretty crazy stuff.
The guy in high school whose name was Legend.
Mike.
Legend?
Yeah.
Yeah, I had there was a guy that went to my high school. His name was I Am a Star. All no spaces.
Did you go to the school?
This was in like the downstate Illinois in the sticks. I mean, I was in the bigger city of the sticks, so like, you know, Rantoul, Illinois. So it was, you know, population, I don't know, 50,000 or something like that. Not a big place. Okay, that makes sense? So no different than when you did hexadecimal math, no different than when you did binary math, no different than when you do decimal math. The only thing that was a difference is, what are we getting the remainder from? We're getting the remainder off of base 10, base 2, in this case, a base 33. All right, so any questions on that? Okay, crap like this will definitely be on the final. In fact, who knows? I might have the entire final of doing addition of all sorts of different bases.
So 37 base.
Huh?
Base 37.
Base 37 would be rough.
Base 128.
Base 1, well, you wouldn't have the conversion back to characters.
You just have to make up the last.
Yeah, I guess you could make up symbols. You have your own mapping.
Custom.
Yeah, what comes after a Z?
So it's probably be rough for
instead
you
of using
grading.
the alphabet, the English or the whatever the alphabet is,
Yeah.
if we go into like say Mandarin or something, would that be?
Do they have more symbols?
I don't know.
We're just assuming.
I'm pretty sure.
I don't know. It just looks like a lot of random crap to me. So Mandarin's got to have more symbols.
Mandarin has quite a few symbols.
I think you
We don't. Do symbols mean words? I mean, we could always go to playing cards. After a Z, you start off with like the 2 of hearts and the 3 of hearts and the 4 of hearts and
So we draw each playing card.
right.
Then you start. Well, after Z, just start using exclamation point at symbol on side.
Well, you can start. You can, if you wanted to keep it. Well, and those would be more than one character. You can create a new single character that is the marrying of, like AA, but maybe do the second A backwards and then like attach them. That's technically. You get what I'm saying? Point is, base 37 is going to get a little random because we're off the end of our
Just
alphabet.
go lowercase.
Could go lowercase, I suppose. All right, it's going to be on the test. Base 4096 math. Make sure you provide your mapping table.
No, it'd be cool if you did that, and then you had it so it was only like
yeah.
A plus 2 or something, and people are freaking out about it, and it's you can do it.
It does sound like something I would do.
Make everyone overthink it.
You know, like even this one. You know, these first 4 were meaningless. I purposely made the second number relatively small relative to the first one, so you only had to deal with the lookups for certain number of spaces. Never did I expect that my genius would have produced such an awesome outcome.
You sure you didn't expect that? You just automatically assume.
Everything I do is just completely awesome. It's just an assumption.
It's gotta be your next cat man.
I have to be careful when I first wake up in the morning. I have to keep my eyes shut for a while because otherwise I take a double take in the bathroom. I just stop when I look at myself in the mirror.
Scared.
No, awesome is what I was. that's what I was going for, but I get it. I get it.
It followed shortly after getting another cat.
What's this?
We started talking about this just after you started talking about your cat.
Did I?
So, well, you
I
mentioned.
mentioned.
Yeah, you mentioned the cat,
No, I never even heard the cat.
I said that's gotta be your next cat name.
and then you were like,
No more cats.
I need to keep my eyes open when my eyes closed when I first wake up. Like, does your cat attack your face when you wake up?
No, my cat would never attack me. My wife, on the other hand, my cat is evil.
Wait, your cat would attack your wife, or your wife would attack you?
My cat would definitely attack my wife.
He's not
That's what I originally
about the
thought.
question.
The way you said that could have gone either way.
No, I see. Okay, so let's start looking at logic gates. Okay, now I want to have the okay, so now we're starting to transition between what we've been doing at the high level in terms of how do computers think to, or how do computers do things to, in terms of math, into how do computers actually represent solutions to problems in circuits. Okay? So we look at something called a logic gate. So we have two initial logic gates, and these are going to match up to what we've dealt with in Java. We have an AND gate and we have an OR gate. Okay? And these guys have pictures associated with them. So AND gate has two inputs, and we'll look at the pictures here in a second. Two inputs, both must be, I'm going to say positive here, or true, for the output. Let's see, for the single output to be positive or true. The reason I'm using the word positive is keep in mind that these things are working off like electrical signals. Okay, so this goes back to what we did early on in the semester with signals. Okay, so we're going to have an on signal, we're going to have an off signal. So positive signal and on signal would represent a true. Okay, so the AND takes in two inputs, and if both are true, the whole thing is true, just like Java's AND. And OR has two inputs, at least one must be positive or true for the single output to be positive or true. Then we have something called an XOR, exclusive OR. Techno geeks might call it a XOR gate. So this guy has two inputs. XOR, I'm sure it's taken. Two inputs, at most one must be positive. Actually, at most is the wrong way of saying it. Exactly one must be positive, true, for the single output to be positive or true. Okay, so OR and XOR are similar with the exception that OR says if any of them or all of them is true, the whole thing's true. So if at least one of them is true, the whole thing's true. An exclusive OR says that exactly one must be true in order for it to be true. So if they're both true, an exclusive OR would be false. Okay? It's one or the other, but not both. OR is one or the other or both. Make sense? Okay. On top of this, we have some other gates, but I'm just going to introduce one of them right now. We have something called a NOT gate. Sometimes they're called inverters. But a NOT gate, one input, output is the inverse of the input. So a positive, true input would result in a negative, false output, and vice versa. Make sense? Okay, so these are kind of our building blocks for creating circuits. Let's look at the pictures of these guys. Okay, so here's our generic thing. We have a gate. So the little chip looking dealie when we deal with these in, if we're actually building circuits. So a little chip dealie that's going to have one or more binary inputs. So one or more digital inputs, either a 0 or a 1 is the inputs, represented as an electrical signal, positive or negative. Okay? On or off. Think of it. However you want to think of it, that's how it works. Okay, so every gate's going to have at least one input, but it may have more. Most of the ones we just talked about have two inputs, except for the NOT gate, which has one input. Right now, what I want to be going through your head is think of these guys like methods. These are reusable chunks of code that take in some number of inputs and produce for us an output. Does that make sense? Okay, it's important. One nice thing about logic gates, when we get to some of the more, well, we won't call them logic gates, we're going to call them combinational circuits. But when we start building gates, putting them all together to create something that does something, we can have more than one output. In a programming language, if we want more than one output, we have to represent it either in an array or another object or something like that. Otherwise we have a single output. That makes sense? For logic gates, we can, or combinational circuits, we can create multiple outputs out of these. But for right now, every single one takes in one or more inputs and produces one output. Okay, so this is what it looks like generically. Here are our gates. So we have the NOT gate, little arrow with a circle on the end of it. So that's the picture of a NOT gate. The AND gate is like the word D, or the letter D. Here's our two inputs, here's our one output. Similar, the NOT gate has one input, one output. Something we want to consider here is the little circle. In terms of this, these images, circle means not. That's the thing that flips it. Because we're going to create some other gates like Nand Gates, which is a NOT AND gate, which will take these two guys and meld them together and basically take this gate right here and just put a little circle on the end. Okay? Similarly, we'll have NOR gates, not OR, to put a little circle there. Okay? There is not a not XOR gate. Because that doesn't roll off the tongue, so they don't make those. Interestingly enough, just from a trivia perspective for what drives the price of memory and technology goes up and down in price, blah, blah, blah. The market is really driven by the current price of XOR gates, and to a lesser extent, NAND gates. Not and. Because all circuits, all of these guys can be implemented in terms of those two. So what companies end up doing is instead of having, a bunch of NOTs, a bunch of ANDs, a bunch of ORs, and a bunch of XORs, a bunch of XORs, they just have a gigantic pile of XORs with maybe some inverters. And now they can produce anything just through that. Okay? The reality of it is anymore, we don't really build our technology through physical gates. We usually prototype it with physical gates, and then we print circuits. So that's why our stuff has gotten smaller. Because believe me, when we do with our cell phones, there would be a lot of gates inside of this to make it do what it does. Probably not what's actually on there anymore. Now we're doing printable circuit boards where all the logic's printed on there, and it works a little bit differently. It's called very large scale integration, VLSI. Okay, so NOT gate, we're going to kind of skim through some of this. We know what that does, right? Not true is false, not false is true, blah, blah, blah. So gives us an example, input 0, outputs 1. Inputs 1, outputs 0. The AND gate, 0 and 0. So false and false is false. True and false is false. False and true is false. True and true is true. So an AND gate only produces a true, only produces a positive output if both inputs are positive. Make sense? That's what that widget does. OR gate is kind of almost the inverse of that. Only produces a 0 when both of them are 0, when both of them are negative. Otherwise, it always produces a 1. Make sense? Well, let me ask you this real quick then. If this is the AND gate, is a NAND gate an OR gate? Is not AND the same thing as saying OR? Is OR and NAND the same. We have something called truth tables. So truth tables would be something weird just happened? Huh? Oh. Well, it's discrete math. That's why you take it as a computer science major. Related. So we have something called truth tables. So the truth table for an OR, we just do a two input OR. So 0 or 0 would produce a what? A 0. A 0 or a 1 would produce a what? 1. A 1 or a 0 would produce a 1. A 1 or a 1 would produce a 1. So that's for a OR. Okay, so I'll just do the NAND next to it. With a NAND, a 0 NAND a 0 would produce a what? Well, 0 and 0 is a 0. Not that is a 1. So we already answered our question, right? A 0 NAND a 1 would be a 0 and 1 would be 0. Not that would be a 1. 1 and a 0. 1 NAND a 0 would be a 1. One NAND a 1 would be a 0. Make sense? So what is the NAND in relation to an OR? These are our truth tables. An OR is always true unless they're both 0. A NAND is always true unless they're both 1. Could we implement an OR using a NAND gate? Let me ask you a follow-up. Could we implement an OR using a NAND gate and an inverter? An inverter would invert all the inputs, right? So 1 NAND 1 would be a what? So here, we're just going to invert the input. So this is a 1 and a 1. This is a 1 and a 0. This is a 0 and a 1. This is a 0 and a 0. So 1 and 1 is 1. NAND, not that, would be 0. 1 NAND 0 would be a 1. 0 NAND 1 would be a 1. 0 NAND 0 would be a 1. Make sense? So an OR gate can be implemented using a NAND gate with inverters for the inputs. Kind of supporting what I said a few minutes ago about companies that make these things. They buy the chips in bulk using the NAND gates, and XOR gates are universal gates is what they're known as. Okay, so those with a little other fluff, inverters and stuff, which are really inexpensive, can help us do a lot of stuff. Okay. So this was our OR. You know what the truth table is for an OR. Exclusive OR, the XOR. Exactly 1 is true for the whole thing to be true. So this one right here, 1 XOR 0 is 1. 0 XOR 1 is 1. In all other cases, it's 0. That's the exclusive OR. One or the other, but not both. Okay, here's the section on truth tables, I guess. Okay, so what's this guy? 3 input truth table. Put the operation in, so a 0 or a 0 or a 0. Now we've advertised our logic gates as only taking in 2 inputs. How would we have a logic gate that took in 3 inputs? Scroll back up here. We look at the generic thing of our logic gates. This guy, where there's 1 or more binary inputs, and then we have our logic gate, then we have our single binary output. But what if I want to have 3 bits of input? I want to have 3 inputs and have them all ORed together. What should it produce? He told me he was leaving early. He's not just ticked. Like, I've had enough of this. You should have totally done that. All right. So I want to have 3 inputs. How would you create that circuit? So it's kind of along the lines of what we just did with the NAND with the inverters to create an OR. How would you do a 3-input OR gate? Assuming they don't build 3-input OR gates. All I've given you is an OR gate that has 2 inputs. Go ahead.
Use 2 OR gates.
Use 2 OR gates. Have the first OR gate for the first 2 inputs, and then have the output of that go into one of the inputs of the second OR gate, along with your third input. So you'd have 2 OR gates. These are AND gates. I don't know why I was circling OR gates, but whatever. So it would look something like this. If we had a 0 or 0 or 0, that's how we'd write it in English. In Java, we would say 0 or 0 or 0. And in Boolean logic nomenclature, we'd say 0 or 0 or 0. Okay? Similarly, I'll just show it to you now since I'm babbling about it. I'm almost positive the book's going to talk about this, but my mind goes in different directions sometimes. So if the book doesn't cover this, this is good stuff. If the book covers this differently, mine's right. I would say an asterisk, but usually it's just a dot. But the only way I can produce the asterisk, produce the thing in the center, is through the asterisk. Asterisk is good enough. So the book either represented as asterisks or a centered dot between them. That's the nomenclature for ANDs. Okay? So that's more just logic stuff. We're trying to mimic a 0 or 0 or 0 or 0 or 1 or, so 3 input things. So we're going to have a single draw with a pen. Oh, so excited about this. Oh no, I'm not going to be able to do this one. Boom.
Say class is over.
Don't act like you're not impressed. Just shut up. I think we all thought that was going to go significantly more south than it did. Uh-oh. Okay. Oh. There we go. Wanted to make sure it was movable. All right, so we have our 2 inputs. Oh. Couple of lines back here. Oh, almost perfect. All right, I'm going to say this is legit. We're going to say that's legit. I'm going to copy that whole thing. Man, you're going to make sure you... actually, we would probably have it down here like this. So you're going to have your two inputs. So 0 or 0 or 0 would look like this. 0 or 0. Or 0. And then we'd wire this onto here. So this would be feed the input of this one. Okay? So this is a 3-input OR gate that we built. Okay. Otherwise, we are going to be reliant on companies to come out with a zillion different logic gates. 2-input ORs, 3-input ORs, 4-input ORs, 5-input ORs. Now, having said that, some of these ones do exist. Not necessarily 3-input ORs, but if there are common gates that are used often, a good example would be an adder. So something we will talk about is something called an adder, which allows us to add, we have a half adder and a full adder. A half adder allows us to add 2 bits together, producing the output, but with no carry. A full adder allows us to add 2 bits together, producing the output as well as the carry. So if you wanted to build, so for example, let's say that we needed a tool for adding 8-bit numbers. Let's just say that's common in building hardware. Given that, somebody could create kind of a super adder, a super full adder, if you will, that basically is 8 adders linked together to produce the ability to add 8 inputs, okay, 8-bit numbers, and produce it as a single gate. Technically, it would be, well, adders aren't logic gates anyways, but technically that would be called a combination circuit. Just like, even though this is a 3-bit OR gate, 3-input OR gate, it still would be called by us a combination circuit that happens to act like a logic gate. Okay? Relatively unimportant, just the difference is what can you buy off the shelf versus what do you have to build. Okay? Questions about this? All right. Notice the XOR gate, picture for the XOR gate, looks just like an OR gate with one extra shallow parabola in the back. See, that, it's like, wait a minute, parabola? Parabola? Is that right? That's a real word. Isn't this a shallow parabola? How else would you describe this? A who? A curved line? That's a parabola. If you were to define parabola, you might say curved line. All right, whatever. This is the XOR. This is the XOR gate. Has the extra curved line in the back. Okay, otherwise it looks just like an OR. But notice the output's different. Okay, we got to our truth tables. Here's a 3-input table. So we just saw how we can build that combination circuit for a 3-input table. 4-input, so on and so forth. Make sense? Okay. So this is all the bit patterns for a 4-input truth table. And that's an important thing. They haven't told us what the function is here. The function here is x. X could be an OR, it could be an AND, it could be a XOR. Could it be a NOT? Why?
Because knots only have one input.
Yeah, NOTs have one input. It's a fixed input. So this couldn't be a NOT.
Well, you could not the final.
Well, you could NOT the final, but you don't know what the operation is yet. So you would need, if you wanted to have a NOT in there, you would have to have a second column here.
Yeah.
But really, you would just have the operation be a NAND gate or a NOR gate, something like that. You would have it as part of it. But if you wanted to do a NOT AND, you could make X an AND and then have another thing that knotted the output. But the point is, an inverter always takes in one input and inverts it. There's no such thing as a two-input inverter. There's a such thing as two inverters, which then take in two inputs, but whatever. Okay, so this would be an example of all the possibilities for 4 inputs. Okay, and make sure you understand this, because this might be related to your homework assignment tonight, which is a programming assignment. Okay, inverter truth table. We have a 0 becomes a 1. So if X is the inverter function, a 0 becomes a 1 becomes a 0. The AND truth table, if X is the AND operator, 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1, so on and so forth. Here's the XOR, only true when exactly one of the inputs is true. The rest of the time it's false. Okay, now something they talk about here, this deals with the taking away from this idea of true or false and moving more into the idea of how power is represented here. So this can also be represented with a timing diagram. So the results of a 3-binary input signal for an AND gate, OR gate, and XOR gate, respectively. AND gates only output on a 1 only if all the inputs equal 1. The OR gate outputs a 1 if any of the inputs equal 1, and the XOR gates output if an odd number of 1s is present. So that would be 0 or in a 2-input 1, an odd number would be 1 or 1. That would be the odd number. Is this for a? Oh, this is for a 3-digit. Yeah, 3-binary input. So if either 1 or 3, if there's either 1 1 or 3 1s, an XOR would produce a true. This is an odd number of 1s. Because you got to consider how it would be built. You'd have an XOR feeding into a second XOR. Okay. So these are your inputs. So they're showing this as a digital input, this as a digital input, this as a digital input. How do you know it's a digital input? It looks boxy rather than curvy. Okay, that's how you know it's a digital input. Okay, so A, B, and C, these are timing diagrams for the output of X. They haven't told us what X is going to be in this. Oh, they told us it's an AND gate in this one. Okay, so X is true when what is the case? When all 3 of these are on high points at the same time. All of them are true. Does that make sense? A OR gate is true under what circumstances? Well, it's true under all circumstances where they're not all in an off state. Okay, so this is the output. Inputs are all over the place, but so you kind of have to draw the picture until it kind of matches up. It's kind of a stupid way to represent it, in my opinion, but that's what this is doing. Okay. here's our combinational circuit stuff. Okay, so for instance, this is A and B fed into an inverter, fed into an OR, with C going into that OR, producing our output X. So what does this do? This is A and B, but really it's A NAND B or C. Isn't this whole thing up here a NAND gate? That's a NAND gate. Okay, and then they kind of give you a real-world application of where this might be used. So for a security system, you have an alarm in your house or something like that. You have multiple sensors throughout the house. You maybe have a sensor on the door, the glass of one of the windows, plus just an outdoor motion sensor. All these guys feed into an OR gate. If any of them fire, if any of them trigger, alarm goes off. But the alarm only goes off if this is a single solid bit going into it, only if it's currently armed. So this alarm is only sounding if this guy is on and one of these things happened, at least. Make sense? So this is a representation of an alarm system using a combinational circuit. Okay, that could be kind of a fair game for a quiz, maybe next class as well. Giving you a scenario, like, hey, let's say you have if I were asking the same question, you have an alarm system that's keeping, tabs on 3 different parts of the house. Draw a combinational circuit that would fire the alarm only when the system is armed. Something like that.
Combination circuit that tracks and make sure all the blinds in your garage are down.
All of them. All the blinds. Okay, so we can have a truth table associated with that particular system. Under what circumstances is the alarm going off? Okay, so this is all the possible inputs. Okay, notice that several of these final ones are in situations where, somebody kicked in the door, the glass shattered, and there's a bunch of people running around outside. All at the same time. Okay? Yeah. I don't think the alarm is going to be this is some sort of assault. And it's The Purge. That's right. Seen that movie? It's a good movie. Didn't they just come out with a sequel? Is that good too? Did you see it?
The second one's better.
Is it?
The first one's terrible.
But still an interesting idea.
Yeah, the second one, they should have done that for the first one because it's all outside.
Okay.
Now it's in one house.
And the idea of the movie Purge is like society has far less crime now than it used to. And the reason for that is one day of the year. It's called the Purge. You can commit any crime, including murder, and there's no consequences.
Oh, God.
So people build up to this one day and then get it all out of their system. And then we're clean for another year. So there's like businesses, like the first one of the guys, his business was in essentially arming your home to protect you from the purge. People would just go, people would spend a lot of money so that their family and stuff could just go into lockdown during the purge and watch the death on TV. So that kind of stuff. Kind of an interesting premise, I think. All right. So here's our combinational logic gates where we have an AND with an inverter. So an AND gate plus a NOT gate is equal to a NAND gate. An OR gate plus a NOT gate is equal to a NOR gate. A exclusive OR, so a XOR gate plus a NOT gate is equal to a NOR gate. Or exclusive NOR gate. So a XNOR gate. That's the one we said that they're not going to make because it doesn't roll off the tongue. Okay. NOT circuits. So similarly, we can do inverters on our inputs, feeding them in to produce different gates. So this has more to do. You probably would not buy a logic gate that looks like this, What they're really showing here is this is a way of drawing a schematic for a gate that is a AND gate. So this guy is an AND gate. We know it's not a NAND gate because the circle's not on the other side. So this guy's an AND gate that takes in 3 inputs, but attached to it, 2 of those inputs, the first and the third, are going to be inverted. That's how you read this. So it's kind of shorthand for circuit diagrams. Make sense? Relatively unimportant. If you like drawing the whole thing out like this, that's fine. Not a big deal. All right, so sample, multi-level combinational logic. So if we have a circuit, if I gave you a circuit like this, so let's just look at A. How do we convert this to a truth table? So one method is to go through each pattern of 1s and 0s at the input and fill in the resulting outputs, the truth table row by row. So for example, here is a combinational circuit that has 3 inputs. Okay? 3 different inputs. So we'll just do this on a slide. We'll call this A. Combo A. Big Mac fries. All right. So possible inputs for 3 digits. We have 0, 0, 0, 0. We have 0, 0, 1. We have 0, 1, 0. We have 0, 1, 1. We have 1, 0, 0. 1, 0, 1. 1, 1, 0. And 1, 1, 1. Those all are possible inputs there. So from a building a truth table perspective, we can get all our possible inputs. If there's 3 inputs, that's a 3-bit number, counting from the smallest unsigned 3-bit number up to the largest unsigned 3-bit number. Those are our inputs. Make sense? Also might come in handy on your homework. Okay. Now, we're just going to do this for A here. So, if our input is 0, 0, 0, so we have 0 going into our AND, and we have a 1 going into our AND, because we're inverting this 0. So this is 0 and 1, which will be a 0. We have 0 or 0, which will be a 0, which then becomes a 0. What's this guy?
There's no circle on it.
Okay. No circle on it.
Oh, it's because I think they like worked through it, kind of.
They did what?
Like,
Basically, there's a circle on the D.
Yeah. They have one here. Circle. So this should do nothing. So that's our output is X. So that's a 0.
I'm saying like those are each like steps. That's what it's saying. Because if you see it's just going up to that first one you see there. That's all it's figuring out in that part of it.
Say this again.
It's the same.
A does one part, B does the next part.
Yeah.
Oh, no, that's fine. But I'm going through this entire... I'm treating this all as just a single circuit.
On D, though, it
Then
does
look at
have
D, yeah.
the circle.
Oh, I get what you're saying. I get what you're saying. So this is our final circuit.
Yeah.
So it is the inversion.
I still don't know why they wouldn't show the circle though.
Yeah, why wouldn't they draw it each time? So 0, 0, 1. So we'll just do it on this one down here. 0, 0, 1. So 0, 0 is always going to be a 0 here. Okay. Would we ever get a 1 here? 1, 0. So the only situation we'd ever get a 1 here is when we had a 1, 0. Okay. So right now we have 0, 0, 1. So 0, 0 is going to be a 0. 1 is going to come in here. It's going to produce a 1, which is then going to produce a 0. Correct? Now, when would this OR not produce a 1? We have a single bit going in here. Would all situations where that's a 1, would this guy produce a 1? The AND gate here.
Or
Yes, the OR gate. Would all situations where this third input was a 1, would this OR gate, just the OR gate, would it produce a 1?
Yes, it's not an exclusive one.
Okay, then we would not that. So we could go through and every single time our third input is a 1, we can say our output is a 0. Because this is really a NOR gate. Output 0. Uh-oh. Output 0. Output 0. Output 0. Every one of those. So all the times where our last bit is 0, we're going to be reliant on the first bit to give us the 1. So Abe, you told us that the only time this will produce a 1 is when what's true?
The top one's a 1.
Top one's a 1, and the second one's a 0. So 1, 0 is the only time this would give us a 1. That's a 0. All right. So that means that this was 1, 0, which will produce a 1 here. 1 or 0, or 1 or anything, is a 1 inverted to a 0. Which means that all other situations, it's a 1. Make sense? So by looking at our circuit, we're able to tell what the necessary output would be by being smart about it and understanding that this guy is feeding into this gate over here, which is going to produce an output regardless of what this guy is. So every single time that this third input's a 1, we're getting a 1 out of this AND gate regardless of what crap happens up here. Make sense? Okay. So another fair question for a quiz could be me showing you a gate and having you tell me what the truth table is for it. Okay, and realistically, if I show you a complex enough gate, well, even if we showed you this one, if you had literally gone through every combination of 3 inputs and walked through the entirety of it by hand, it would have taken a lot more time than what we just did, right? Okay, so if you have a quiz and the quiz is only a 3-minute quiz, you might want to do what we did rather than walk through it logically for the whole process. Were these the outputs of it? 1, 0, 1, 0, 0, 0, 1, 0. Yeah. So we just checked our work. Okay. That's the end of a whole chapter. One class. All right. So let's start the next chapter. Well, you see how these go pretty quick, right? So that's why we had time here at the end to do logic gate stuff, because logic gates go pretty quick. We're learning a new programming language. That's the mentality we should have here. Except you're not having to learn syntax, like an if statement or a while loop or something like that. You're learning some logic gates, and now it's a matter of being inventive and putting them together like Legos. All right. Lincoln Logs. Do they still make Lincoln Logs?
I don't know. I haven't.
They do? I almost killed my brother one time with a snapped in half Lincoln log. Those things splinter.
They just had an article posted that they're moving the factory from China over into America, and they're only doing American Lincoln logs because it was made in China.
They're only doing American Lincoln logs? What does that even mean?
Well, I mean, like they're made in America now, so they're still.
I gotcha, but would they still sell them in China?
I don't know if they did something in China.
What about the lead paint? I missed the taste of it.
It stunted his growth. Is that what happened?
That and coffee.
That and coffee? Well, I don't know. I drink a lot of coffee, and I'm
I
tall.
started drinking coffee at 10.
I didn't start that young. I started programming before I started drinking coffee. Started programming at 9.
I played outside.
Yeah, probably coffee at 15 or 16 might be my guess. Nowadays, you got junior high people going to Starbucks, right? So you're almost encouraged into coffee earlier.
I like drinking hot coffee.
Coffee shops didn't
Yeah,
really.
the people that go to Starbucks at 15 or 16 are getting that frilly white chocolate mocha.
Well, that's fine. It's still the gateway drug. It's the gateway. It's the gateway drug to black coffee. This is what it is.
No, espresso in coffee. Take a lot of it.
That's disgusting.
And an IV.
You either have espresso or you have coffee. You don't mix them.
Called red eye.
It's called disgusting.
Americano.
That's not Americano.
Americano is espresso with water on top.
That's an American Americano.
It's a diluted, it's diluted espresso shots.
An Americano is actually with alcohol. A real Americano.
It's with alcohol?
Yeah.
I've never heard that
I
before.
know about this.
It is in Italian. It's if you order an Americano in Italy, you will get something
With alcohol in it. I get it. Is that because they're messing around with Americans?
Yeah, it's like, Americans just like their coffee just weird, so.
2 shots of espresso and 16 fluid ounces of moonshine. You drink this American.
Wake you up and put you down.
Oh, yeah. Okay. So, now we're back to Boolean expressions. Actually, I want to give you your class out at 20 or 25? 25. 15. Here, let's do this. I'll give you your homework assignment now, and then we'll start this chapter. Oh, I already had it open, it looks like. Well, that's good. Remember that? When I come in and change your grades, steal my laptop, log in.
Does Safari keep it in plain text too?
I would hope not.
Firefox does.
Really? Oy.
That's
I don't know if Chrome does it.
All right, homework number 10. Write a Java program which implements the logic gates and or XOR and not. Let's see, and or XOR not NAND nor. That's all I want. Yeah, not XOR. All right, so you're going to implement all of these logic gates for and or XOR, not NAND, NOR, and NUXOR. It's a guttural. NUXOR. Okay, so implement all these in Java. So probably you want a method for each of these. So how about implements methods for the following logic gates. Then display the 2 input truth table for each of these logic gates. Make sense? So you're going to write methods for each of those logic gates. So the AND, OR, XOR, NAND, NOR, and NUXOR should all take 2 inputs, 2 bits. NOT should take just 1 to invert something. All right. Then you need to have a generate truth table method or procedure or something like that. Something that will allow your program to output the truth table for each of those gates. Make sense? All right, so that's the assignment that is due on Tuesday. And like I said in my other class this morning, if you do well in that assignment, work hard at it, and the class as a whole does a good job on the quiz I'm going to give you on Tuesday, I may not give you homework over Thanksgiving break.
Still not definite.
Huh?
Still not definite.
Okay, I won't give you homework if you perform well on the homework and on the quiz.
How will you know homework?
If you do give us homework, we have the right to go to your house.
For-
Get mad at you.
Well, that's fine, whatever.
Peek inside the window.
Hey, you're going to knock at least 3 times before you open the garage. All right, so that's the homework assignment due Tuesday. Let's spend just a couple minutes starting this chapter, because this one's another fairly short chapter. Okay, so need for Boolean expressions. What's a Boolean expression? Any expression that boils down to a single value of true or false. Evan, you're already packing up? I'm still talking. Shouldn't be taking notes?
I said that to myself.
All right, so in any case, why do we need these guys? Okay, we have 2 methods for representing combinational circuits. Schematics and truth tables. So schematics are our little picture drawing stuff, which is my preference. Then you have truth tables, which are stupid. Also going to be on the test. Which of these is stupid? I like the pictures. All right, so but these are 2 different ways that we can represent combinational logic. Okay? So these 2 methods are inadequate for a number of reasons. So both schematics and truth tables take too much space to describe the operation of complex circuits with numerous inputs. So we can see pretty quickly that as we start making, really, this thing does next to nothing, right? So think about this. This really does nothing. And here's the representation of nothing. So if this does almost nothing, and this is the representation of almost nothing, if we had something that did something, the representation would be ridiculous, right? Okay, so these guys are inefficient for describing logic. Okay, that doesn't mean they're not accurate for describing logic. They're just inefficient for describing logic. Okay, so these take up too much space in the operations of complex circuits with numerous inputs. The truth table hides circuit information. So at a glance, you can't see what kinds of circuits, what kinds of logic gates we're going to need to build this. Okay, because it's all hidden inside these numbers. So if you just look at these 2, this first one's more expressive than the second one. Clearly, right? Okay, thirdly, the schematic diagram is difficult to use when trying to determine output values for each input combination. That's kind of what we dealt with when we were looking at the example a couple minutes ago, building out that truth table. We had to find our shortcuts based on our human logic, able to look at the input to the OR in order to make it palatable. And certainly as the number of inputs grows and the complexity of our combinational circuit grows, building a truth table by hand is going to become crazy. Make sense? Okay. Ha-ha! Dot. Remember I said, score, Christian worldview. Thou shalt not boast.
You have the Christian rule because Abe is present.
That's right, it's by default. Okay, so we'll come back next time. We'll look at the symbols for Boolean algebra, which I've already introduced, and we'll power through this chapter as well. We'll also look at the homework assignment. All right, I will see everybody on Tuesday.